So transition state theory, also called absolute reaction rate theory. This theory was first proposed by Marsellin in 1914, and the theory was further developed by Eyring and Polanyi, in 1934. According to Eyring, they proposed a mechanism for transition state theory. What is that? The reactant molecules. First we are going to discuss the transition state theory for gas phase reactions. So here A is a gas, B also a gas. First we are going to see the reaction for, we are going to apply the theory for gas phase reaction. After that we will come to solution phase. So here A and B are reactant molecule. They combine and form an activated complex. Between the reactant molecule and the activated complex, there is an equilibrium. This is not a normal equilibrium. It is called a quasi-equilibrium. Listen, A and B are normal molecule, whereas this X double dagger is the activated complex. Then this activated complex decomposed to give the product. This is the mechanism proposed by Eyring and Polanyi. Now, what is the difference between an activated complex and a normal molecule? Activated complex differ from normal molecule. In one of the particular one of the particular degrees of freedom, that is, activated complex has one vibrational degree of freedom less than the normal molecule. Activated complex has one vibrational degree of freedom less than the normal molecule. So keep this point in mind, very, very important. Right now, so according to transition state theory, rate of a reaction is equal to, it has two terms. One is the frequency of the activated complex, one particular frequency through which the activated complex is transformed into product. So this is one particular frequency, sometimes it is called as magic frequency. Through this magic frequency, the activated complex is transformed into product. And what is this X double dagger square bracket? The square bracket containing X double dagger is nothing but concentration of the activated complex. This is equation number 1. Then we know very well there is a quasi-equilibrium, right? So in the previous page I showed you, there is a quasi-equilibrium. So for that equilibrium, we can apply what is called the equilibrium constant idea, or the law of mass action. So we can find the equilibrium constant for this equilibrium. So what is equilibrium constant for this? The concentration of the equilibrium constant for the activation reaction, which is represented as K double dagger, is equal to concentration of the activated complex divided by concentration of the reactant, the product of the concentration of the reactant molecules. We want the concentration of the activated complex. So if you rearrange this equation, we get the concentration of the activated complex equal to, bring A and B to the left hand side. So we get K double dagger A into B. Then the frequency of the loose vibration or the magic vibration. We can obtain this from partition function equation, but I am not going to show that now. But remember, the frequency of the vibration is equal to kBT by H. So this is the concentration, this is the frequency. Substitute these values here. You will get rate is equal to kBT by H, K double dagger into concentration of A into concentration of B. Listen, here we are assuming one important thing. What is that? We are assuming that all activated complex, forms product. But it is not necessary, right? It is not necessary that all activated complex to form product. Are you able to follow? Right, so So we need to introduce one more term here called kappa. Kappa. What is this kappa? This kappa is called transmission coefficient. Take note. The kappa is called transmission coefficient. Okay. If all the activated complex transformed into product, then transmission coefficient is 1. But most of the time, if you see, right, the transmission coefficient value is not equal to 1. It is less than 1. Okay, right. So I'm just introducing one more term here. Okay, this term is what we call as transmission coefficient. Transmission coefficient is 1 if all the activated complex is converted into product. Okay, now we also know that experimental rate is equal to, since two molecules are involving, we can write experimental rate as rate constant into concentration of A into concentration of B. Okay, then I'll take this as equation number 3. Since these two are one and the same, so let me equate the right hand side. So to equate the right hand side, we get an expression like this. Let me include the kappa also here. Kappa. This kappa. Kappa into KBT by H into K double dagger. Okay, and we know that delta G naught double dagger equal to minus RT ln K. Right, then bring this RT to the left hand side. This is equal to ln K double dagger. Then what is K double dagger? If we remove log, this entire quantity becomes e power exponential power term. Okay, so K double dagger equal to e power minus delta G naught double dagger by RT. Substitute this in the equation 4, so you will get rate constant equal to kappa into KBT by H into e power minus delta G double dagger by RT. Okay, if I substitute, delta G naught is nothing but delta H naught minus T delta S naught. If I substitute this in this equation, right, we get rate constant equal to KBT by H into e power minus delta H naught double dagger by RT into e power plus delta S naught double dagger by R. Okay, so this is the rate constant expression for a bimolecular reaction taking place in gas phase. Okay, and remember, I left one term. I introduced a new term here that is called kappa. Kappa is nothing but transmission coefficient. Okay, yeah. Now, so this is the rate constant expression. This equation is what we call as Wien-Jones-Eyring equation. Right? Now, if you compare this equation with the Arrhenius equation, right, what result we get? Arrhenius equation is K equal to A into e power minus EA by RT. And if you take logarithm, you will get ln K equal to ln A minus EA by RT. If I differentiate this with respect to temperature, I will get EA by RT square in as equation 1. In the case of transition state theory, this is one of the steps actually. K is equal to kappa. Let me introduce kappa also. Kappa into KBT by H. If I take logarithm, I will get ln K equal to ln kappa. I will introduce kappa here. Kappa into this, kappa KB into kappa by H plus ln T ln the K double dagger. If I differentiate, this entire quantity becomes 0. Remember, kappa value is a constant for a given reaction. So, KB into kappa by H, the entire quantities are constant. By differentiation, it becomes 0. Ln T equal to 1 by T, and if I differentiate this, I will get d ln K double dagger by dt. Right? So, I have d ln K by dt here. Here also I have d ln K by dt. Right? According to Van 't Hoff equation, we can write d ln K double dagger, equilibrium constant, right? K double dagger by dt as delta U naught double dagger by RT square. Okay. Now, by comparing these two equations, we can write 1 by T into delta U naught by RT square equal to EA by RT square. If I rearrange this, I will get an expression for delta U naught. Yes, we get, last class we discussed this, we get delta U naught double dagger is equal to EA minus RT. What is delta U naught? It is nothing but change in standard free energy, or I can say standard internal energy change for the activation reaction. I repeat, standard internal energy change for the activation reaction is equal to activation energy minus RT. So if you know the experimental activation energy, and if you subtract R and T, or R into T, okay, you will get what is called delta U naught double dagger. From this, you can also calculate delta H naught double dagger by making use of this relation. Okay, so we get delta H naught double dagger equal to delta U naught double dagger plus RT into delta Ng. Right? If I substitute this delta H naught double dagger in the Eyring equation, okay, by substituting, see, I'm just making some rearrangement. We discussed this in the last class. Delta H naught double dagger equal to EA minus MRT, where M is nothing but 1 minus delta N double dagger. If M is equal to 1, it is unimolecular reaction. If M is equal to 2, it is bimolecular reaction. Okay? Yes, these things we discussed in the last class. Right? If M is equal to 2, it is called bimolecular reaction. If I substitute delta H naught double dagger in this place, and if you make some rearrangement, yes, we end up with this expression finally. Okay, this is what this is where we stopped our last session. Okay. In collision theory, you know very well. I'll just compare collision theory and transition state theory. Okay, collision theory. According to collision theory, the rate constant K is equal to a steric factor P into collision frequency ZAB into e power minus activation energy from collision theory EC by RT. Okay, this is the expression for rate constant from collision theory. Now, from transition state theory, I'll just write shortly as TST, transition state theory. Rate constant K is equal to kappa, here also we should put kappa into KBT by H, okay, into e power delta S naught double dagger by R into e power minus delta H naught double dagger by RT. Okay, take down. We know very well delta H naught double dagger is equal to EA minus M into RT. Okay, in the last class I showed this. Substitute this here and you will get another alternative expression for transition state theory, which is nothing but K is equal to kappa into KBT by H. Okay, observe carefully. Kappa into KBT by H into e power M. Last class we discussed this. E power M into e power delta S naught double dagger by R into e power minus EA by RT. Now, listen, if I compare these two, this is activation energy from collision theory, this is activation energy from the experimental, right? This is experimental activation energy, actually called Arrhenius activation energy. If I compare these two, right, that is this with this with this, listen, these two terms, suppose if these two terms are equal, then P into ZAB is equal to kappa into KBT by H into e power M into e power delta S naught double dagger by R. Okay, take down. Very, very important. Take down. See, by comparing the above two equations, see, if you compare this equation and the collision theory equation, if you compare these two, we can write P into ZAB. Sorry, if you compare this and this, you will get P ZAB equal to this. Assuming this collision theory activation energy calculated from theoretical method is equal to the activation energy from experiment. Just and just approximate or assume that these two are equal. If you make these two values are equal, then this quantity should be equal to P into ZAB. Okay, and here this term kappa into kBT by h into e power m, this term has a unit of frequency. Actually, kappa no unit, e power m no unit, but this kBT h has the unit of frequency. Okay, and in the left hand side, ZAB has the unit of frequency. Therefore, ZAB should be equal to this quantity, and e power delta S double dagger should be equal to the stirring factor. Okay, so by making use of that idea, we can write ZAB equal to kappa into kBT by h into e power m, and P is equal to e power plus delta S naught double dagger by R. Okay, take one. Transition state theory from statistical mechanics. From statistical mechanics, that is using partition function, very specifically using partition function. Okay, this also we can do. Okay, now listen carefully. Suppose I take some reaction A plus B in gas phase, A plus B forming an activated complex and giving a product. Right, here we have a quasi-equilibrium, so there is a quasi-equilibrium constant K double dagger. Okay, this quasi-equilibrium constant, okay, can be related to the partition functions, but I am not going to do that. Okay, but the derivations are available in almost all books, so I'll just leave this to you as an exercise. You try this, and I'm going to write only the final expression. What is the final expression? Listen, rate constant K is equal to kappa, where kappa is the transmission coefficient, into kBT by h into the partition function of the activated complex divided by partition function of the molecule A into partition function of the molecule B. These are all actually called total partition function per unit volume. Okay, into e power minus E naught by RT, where this E naught is the activation energy per mole. This is activation energy per mole of the compound. Okay, E naught. Q double dagger, QA, QB, these are all partition functions of the activated complex and the reactant molecules. Listen, Q is the total partition function. Keep this in mind. Total means translation, rotation, vibration, everything. Okay. Q double dagger indicate partition function for the activated complex. QA and QB are partition functions of the reactant molecules. Right? Take two. Now we'll compare this equation with the Arrhenius equation and transition state and collision theory equation. Okay. First, let me compare with Arrhenius equation. Right. So, comparison. Number one with the Arrhenius equation. See, you know very well. From transition state theory, using partition function, we derived the expression for rate constant K is equal to the transmission coefficient into kBT by H into Q double dagger by QA into QB into e power minus E naught by RT. Okay, this we know, this is from transition state theory. Using partition function, we arrived at. Then from Arrhenius equation, we can write rate constant equal to 3 exponential factor A into e power minus EA by RT. Okay, let us assume this EA and this E naught are same. Okay, actually this E naught comes from quantum mechanics. This is experimental EA. Let us assume that these two are equal. Okay, these two are equal. If these two are equal, then 3 exponential factor should be equal to this quantity. So remember, 3 exponential factor A is equal to the transmission coefficient into kBT by H into Q double dagger by QA into QB. Take note, this is the pre-exponential factor A, how it is related to the partition function, okay, equation from transition theory. Right? Take note. To how to compare this with the collision theory. This is very, very important. Okay, try to keep this in mind. Both are very, very important. Right? With the collision theory, listen. From collision theory, you know very well, rate constant K for a bimolecular reaction involving unlike species is equal to steric factor P into collision frequency ZAB into e power minus collision activation energy by R. Let us assume that this quantity and this quantity they are same, they are equal. Let us assume. If they are equal, therefore P into ZAB should be equal to kappa into kBT by H into Q double dagger by QA into QB. In this quantity has the unit of frequency and that should be compared with ZAB. Therefore, I can write ZAB, that is collision frequency, is equal to kappa into kBT by H. Kappa into kBT by H, this is collision frequency. And what is steric factor? Steric factor is equal to this quantity Q double dagger by QA into QB. Take down, very, very, very important. How to calculate steric factor for, using partition function values. Okay, yes, it is possible, we can calculate, right? And this is the expression, try to remember this. Okay. Take down some of the approximate values of the translation partition function, rotation partition function and all. Okay. The typical values of translation, rotation and vibrational partition functions are, listen, what are the typical values? Typical values of translation partition function QT, rotational partition function QR and vibrational partition function QB. We use these three partition functions in chemical kinetics theory or transition state theory. Okay, what are the typical values? Listen, for each, observe carefully, for each translational degrees of freedom, for each translational partition function, okay, what is the contribution? For each translation partition function, what is the contribution? Let me write here. Contribution to the rate constant, to K. Contribution to K. K is actually 10 to the power 9 to 10 to the power 10 decimeter inverse. Okay, take note down, very important. For each rotation, what is the typical value of their contribution? Okay, for each rotation, the value is 10 to 100. 10 to 100. And for each vibration, the value is 1 to 10. These are some typical values, try to remember this. Right? Now, we'll do some problem here so that you can understand what is the purpose of discussing all these things. Okay? Take note. Listen. Take down this question. See, at 298 Kelvin, okay, at 298 Kelvin, using the typical values of the translation, rotation, vibration. Okay, let me give some value for this particular problem, right? Say translation partition function contributes 5 into 10 to the power 9 translation. Then for each translation, I'll give some value. This will be in the range, right? 10 power 9 to 10 power 10. Then each rotation I'll give some value in this range, 10 to 100, so I'll give say for 50, and each vibration, right, I'll take this value as 5. Between 1 to 50, I'll take 5. Okay, I'm just taking the half value. 10 power 9 to 10 power 10 means the middle value is 5 into 10 power 9. 10 to 100 means the middle value is 50, roughly. And I'll take this as 5. Now listen, now what we have to do, listen, we should calculate, okay, the pre-exponential factor A. We need to calculate pre-exponential factor A for the following reactions. First, reaction 1, atom plus atom plus atom form an activated complex. For this reaction, what's the value of the pre-exponential factor? And second question, atom plus a linear molecule, atom plus a linear molecule form activated complex. Assume that the activated complex is non-linear. It forms non-linear activated complex. Then 3, atom, okay, instead of atom, I'll take two non-linear molecules. 2 non-linear molecules form, okay, non-linear activated complex. Non-linear activated complex. Now the question is, we need to find the value of pre-exponential factor A for these reactions. Okay, yes, how to do? Let us start with the equation reaction 1. Okay, I'll just show you how to do this. Very easy, but you should know the methodology. Okay, yeah, let me proceed. Right, listen. So the given reactions, the number A, the first reaction is atom plus atom. One atom combined with another atom form an activated complex. You know very well, 2 atoms combined, it should be linear only. There is no other possibility, it should be linear. Okay, listen. We know very well the pre-exponential factor A is equal to kappa into kBT by H, right, into Q double dagger by QA into QB. This we know. And yeah, I forgot to give this information also. Right? Let us also assume that transmission coefficient is 1. Meaning all the activated complexes are transformed into product. That's the meaning. Transmission coefficient is 1. Let us assume like that. Now, see here. So, kappa value is 1. Right? At 298 Kelvin, the value of kBT by H, remember this value? At 298 Kelvin, the value of kBT by H is equal to 6.2 into 10 to the power 12 second inverse. Okay, even if you don't remember the 6.2, at least remember this 10 power 12, that is important. 10 power 12 second inverse. This is the value of kBT by H at 298 Kelvin. Okay, now we'll substitute these values here. So, kappa value is 1. What's the value of kBT by H? 6.2 into 10 to the power 12 into Q double dagger. Listen, total partition function of the activated complex. Total partition function of the activated complex equal to, listen, whether it is a linear, non-linear, whatever it is, all species, whether it is normal molecule or activated complex, whatever it is, all species have 3 translation degrees of freedom. Okay, so QT into QT into QT, I can put directly QT cube. It has 3 translation degrees of freedom. Then, see, we get a linear activated complex. Okay, the 2 atoms combine and form linear activated complex. So, you have a linear. In the case of linear species, there are 2 rotations possible. So, one rotation QR, another rotation QR, QR into QR become QR square. Right? And that is, listen, when the 2 atoms, suppose I'll take one atom as say B, another atom also as B, if they associate, yes, there is a bond-like situation happens. Okay? Right? So when there is one bond, there should be a vibrational degree of freedom. But you know very well, activated complex has one vibrational degree of freedom less. So, since there is a bond, there should be one vibrational degree of freedom. But it is an activated complex, so that vibrational degrees of freedom becomes 0. So, there is no vibrational degrees of freedom. Okay, and what about the normal molecule Q and QB? QA. QA is an atom. For atom, only translation available. Okay, and QB, only translation available. Okay, listen. The vibrational partition function for the activated complex. Let me explain this. Number of degrees, number of vibrational degrees of freedom. Number of vibrational degrees of freedom of an activated complex, okay, is equal to, we have two equations here. One is 3n minus 6 for linear, 3n minus 7 for nonlinear. This formula is applicable for activated complex. For linear it is 3n minus 6, for nonlinear it is 3n minus 7. Since we are getting linear complex here, use this formula, put n equal to 2. 2 into 3, 6, 6 minus 6 is 0. There is no vibrational degree of freedom for the activated complex here. Therefore, I didn't put any QV here. Okay, only QT, QR are there. No, there is no QV. And in the denominator I have atoms. For atoms, only translations are possible. No rotation, no vibration. If I substitute all this data here, what will happen? See, A is equal to, I'll do 6.1 per 12. So what is Q double dagger? Q double dagger equal to QT cube into QR square by QT cube into QT cube. So 1 QT cube cancel. So what we get is A is equal to 6.2 into 10 to the power 12 into QR square by QT cube. Observe carefully. QR square by QT cube. Listen, what is the contribution of QR? Each rotation degree of freedom contributes. In the problem it is given. Each rotation degree of freedom contributes 50. So, in the place of QR square, you put 50 into 50 divided by, and I have QT cube here. For each translation contribute 5 into 10 power 9. So, 5 into 10 power 9 into 5 into 10 power 9. Okay. Now, we need to simplify this. How to do that? See, 1 5s are for 10 5s are 50, 1 5s are for 10 5s are 50, right? So the answer is A is equal to 6.2 into, right? Here I have 10 power 18, here I have 10 power 32, 10 power 32, here I have 10 power 18. If I bring it to the numerator, it becomes 10 power minus 18. 32 minus 18 you subtract and tell me what will be the answer. Yeah, I just made a mistake. Listen. I have QR square here, so I'll put 50 into 50. But in the generator, I have QT cube, no. 5 into 10 power 9, 5 into 10 power 9, and one more 5 into 10 power 9, I forgot this. I'm sorry, just take 2. Okay, so if I divide this 5, 1 5 are 5, 2 5 are 10. Now what will be the answer? 2 into 6.2, I'm sorry, 2 into 6.2, 2 to 4, 6 into 2, 12, 12.4 into, now I have 10 power 22, here I have 10 power 22 in the numerator, and denominator we have 10 power 9 plus 9 plus 9, 27. If you bring it to the numerator, it becomes minus 27, so it becomes 10 power minus 5. Okay, if I divide this by 10, I will get 1.24 into 10 power minus 4. Yes, is this correct? Let's check it. Is this correct? Here I have 10 power 12. Oh no. Sorry. So this is just 10 power 12, right? 10 power 12. And here we have 10 power minus 27. If I subtract, I will get 7, 5, 1, 15. 10 to the power minus 15. Right? And if I divide by 10, it becomes 10 power minus. Let me do it in the next page. Okay? This I will write clearly. Observe carefully. So A is equal to kappa value is 1, kBt by h is 6.2 into 10 to the power 9. Sorry, 10 to the power 12. This is the value of kBt by h at 298 Kelvin. And we have 2 rotational degree of freedom. Each rotation will contribute 50, so 50 into 50. And there are 3 translation. So for each translation, 5 into 10 power 9 is the contribution. So there are 3, so 5 into 10 power 9, 5 into 10 power 9. Okay, 1 5s are 5, 10 5s are 50, 1 5s are 5, 10 5s are 50. Okay, then 1 5s are 5, 2 5s are 10. If I multiply this by 2, I'll get 12.4 into, here I have, see, observe carefully, here I have 10 power 12. Here I have 10 power 1, correct? 10 power 1. In denominator, I have 10 power 9 plus 9 plus 9, 10 power 27. If we bring it to the numerator, it will become 10 power minus 27. So what we get is 10 power 3, 10 power minus 27, 10 power 13, 10 power minus 27, I'll get 10 power minus 40. Now, if you write in the standard form, divide this value by 10 and multiply by 10, you will get 1.24 into 10 power minus 13. Okay, yes, this is the pre-exponential factor. Okay, take it. Yeah, second question, listen. So, second question, before going to the second question, let me write the expression. Listen, the pre-exponential factor of Arrhenius equation is equal to kappa into kBt by h into q double dagger, partition function of the activated complex by partition function of the reacting species. Now, what is the second reaction given? The second reaction is question. Yeah, atom plus linear molecule. Let me write here. This is the question. Atom plus a linear molecule form a non-linear activated complex. Okay, take it. I'll check the question once again. Yeah, take it. Yes, we can do this problem. How? See. And you know very well, kappa value is given, which is 1, and kBt by h at 298 Kelvin, okay, the value is 6.2 into 10 to the power 12, okay, I'll repeat, 6.2 into 10 to the power 12, second inverse. I told you, kBt by h as the unit of frequency. Remember this, okay, and this is the value at 298 Kelvin. Now you need to focus on Q double dagger, Q and QB. Right, first I'll write the activated complex Q double dagger. Q double dagger is a non-linear activated complex. For any species, translation should be 3. Always translation should be 3 for any species. Then, since it is non-linear, there are 3 rotational degrees of freedom possible. So QRQ. Then, activated complex, since it is non-linear, number of vibrational degree of freedom is 3n minus 7. Non-linear means 3n minus 7 for activated complex. Okay, now how many atoms, that is not mentioned. So what I am going to do, I'll just take q power 3n minus 7. Q power 3n minus 7 vibrational degrees of freedom should be there, QB. This is for activated complex. Now we'll come to the molecule A. So listen here. A is nothing but atom. Suppose I'll take this is A, this is A and this is B. A is an atom. For atom, only translation is possible. So 3 translation degree of freedom. Then what about linear molecule QB? QB equal to, for any molecule, for any species, there are 3 translation, and it is linear. So there are 2 rotation possible. Okay, and it is this is normal molecule. For normal molecule and it is linear, so how many vibration? 3n minus 5. Okay, so I'll put QV 3n minus 5 vibration degree of freedom. I'll substitute all these things here. So what is A? Therefore A is equal to, kappa value is 1, kBt by h is so 6.2 into 10 to the power 12 into Q double dagger. What is Q double dagger? QT cube, QR cube, and QV power 3n minus 7 divided by QT cube. This is for A, and for B, QT cube, QR squared into QV power 3n minus 5. Take. Listen, what is the notable point here is, listen, one atom combined with a molecule, a linear molecule. Let us assume that the molecule has n atom. Okay, which form a nonlinear activated complex. In this case, for the activated complex, how to find the vibrational degree of freedom. Okay, vibrational degree of freedom, listen, I have n atom plus 1. So, there are n plus 1 atoms. This activated complex is n plus 1. N plus 1. Okay, multiply this by 3 and subtract 7. Because you know very well, vibrational degree of freedom has, the activated complex has 1 vibrational degree of freedom less. So, instead of minus 6, you put minus 7. Correct? And if you simplify this, you will get 3n plus 3 minus 7 will get 3n minus 4. That's why I put 3n minus 4 here. And for normal molecule, it is 3n minus 5. Okay, that is for B. B is a normal molecule. For normal linear molecule, number of vibrational degree of freedom is 3n minus 5. So QV power 3n minus 5. Right? Is this clear to all? So, yeah. Observe this carefully. So, what is the value of A? A is equal to 6.2 into 10 to the power 12 second inverse into, now let me cancel some of the terms here. See, 1 QT cube cancels here. QR cube, QR square are there. So if you cancel QR square, this cube will go away. So I'll get 1 QR. 1 QR term will be there. Then, see, if I bring this term to the numerator, what will happen? See, in the numerator I have QV power 3n into QV power minus 4. I can separate this like this. And if you bring it to the numerator, I'll get QV power minus 3n and QV power plus 5. Okay, so these two cancel each other because not cancel. QV power 0 is 1, so that becomes 1. Here I have QV power minus 4. Here I have QV power 5. So what we get is just 1 QV, right? So what we get is QR, 1 QR in the numerator and 1 QV in the numerator divided by 1 QT cube in the denominator. 1 QT cube in the denominator. Okay, just check it. So if I substitute the value of, see, after simplification we get this. Now if you substitute the values of these contributions, okay, and if you simplify, you will get the answer as 1.24 into 10 to the power minus 14 decimeter cube per second. Okay, take note. The third type of reaction. What is the third one? In the third one, I have given two non-linear molecule. Okay, I have molecule A which is non-linear, and I have another molecule B. This is also non-linear, and they form an activated complex. An activated complex. This is also non-linear. Okay, but number of atom is not given. Let us assume A molecule has n atom of A and B molecule has n atom of B. NB. Na atoms of A, NB atoms of B. Okay, now listen. So what's the formula? You know, A is equal to kappa into KBT by H into Q double dagger by QA into QB. This is the formula for pre-exponential factor. K value is 1. KBTH is at 290 Kelvin. It is 6.2 into 10 to the power 12 second inverse. Okay, this is value you should remember. Q double dagger, observe carefully. Now it is an activated complex. Non-linear. How many atoms are there? Listen, here I have Na atoms, here I have Nb atoms. So they combine and form Na plus Nb. This is the total number of atoms. multiply this by 3 minus 7. Are you able to follow? You know very well, any species has 3 translation, so QT cube, and it is non-linear, so 3 rotation, and number of vibration QV is this value, that is 3 into Na plus Nb minus 7 divided by, and here this is also a molecule, so there are 3 translation and it is non-linear, so 3 rotation, okay, and non-normal molecule, number of vibration is, vibration you have QV equal to QV, 3n minus 6 you should put, so 3 into Na, number of atoms in this molecule is Na minus 6, into, now we'll come for B molecule. B molecule also has 3 translation, non-linear molecule, so there are 3 rotation, and B is also a normal molecule. For normal molecule, is this visible? Is this visible to all?
Yes, sir.
Okay, good. Now, yeah. So 3 translation and non-linear molecule, so 3 rotation. Number of vibration, listen, this molecule has Nb number of atom, so number of vibration in the atom QB equal to 3 into Nb atoms minus 6. Now we'll simplify this. Listen, QT cube, 1 QT cube cancel, QR cube, 1 QR cube cancel. So what we left with is 6.2 into 10 to the power 12 into, okay, here I have, see, I'll write this in a clear manner, QV, I'll multiply by 3, so 3 in Na plus 3 Nb minus 7, okay, and I have QB power 3 Na minus 6, if I bring it to the numerator, I'll get minus 3 Na plus 6. Similarly, if I bring this term to the numerator, I'll get minus 3Nb plus 6. Okay, divided by QT cube, we keep it as such. QT cube and QR cube are there in the denominator. You just keep them as such. Now see here, 3Na cancel, plus 3Nb minus 3Nb cancel. Then we have minus 7 and plus 12 here. Minus 7 plus 12. So what we get is, yes, tell me what we get. How many vibration now? Tell me. How many vibrations? Minus 7 plus 12. Hello? Minus 7 plus 6 plus 6 is plus 12. So plus 12 minus 7. How much?
Plus 5, sir.
Plus 5. So there are 5 vibration degree of freedom divided by QT cube into QR cube. Now we'll substitute the values. So what we get is 6.2 into 10 to the power 12 into, what is QV? What is the contribution of QV? Each QV contribute 5, right? 5. So 5 into 5 into 5. There are 5. Okay, sorry. There are 5 vibration degree of freedom. Number 5 is there. So Q5 into 5 into 5 into 5 divided by QT cube. QT cube is 5 into 10 to the power 9. 5 into 10 to the power 9, 5 into 10 to the power 9. Then what is QR? Contribution of QR is 50. 50 into 50 into 50. Right? Up to this, any doubt? Yes. Just simplify this. 1 5 1 5 go away. 1 5 1 5 1 5 1 5. Then 1 5s are 5. 10 5s are 50. 1 5s are 5. 10 5s are 50. Okay. Yeah. Then we have a 50 here. Okay, so what we should do is that 6.2 into 10 to the power 12 in the numerator divided by, I'll just separate this 50, I'll just separate this 50 into 5 into 10. So I'll just put 5. I have 10 here, 10 here, 10 here, 10 power 3, and here I have 10 power 27, so 10 power 30. 10 power 30. Okay, 6.2 by 5, I'll get 1.12. 12 means 2, 20 means 4. 1.24 into 10 to the power minus 18. I'm getting The answer is 1.24 into 10 to the power minus 18. Okay, take note. The next point, how to determine delta H naught double dagger and delta S naught double dagger from experimental measurements, from experiment. Experimentally, how to determine these values? Okay, how to determine these values through experimental methods. Okay, let's have to do that. Listen, you know very well, according to transition state theory, rate constant K is equal to kappa into KBT by H into e power delta S naught double dagger by R into e power minus delta H naught double dagger by RT. Okay, this we know. Right? Now what we'll do, I'll bring this temperature to the left hand side, so I'll get K by T, and we have kappa here, KB here, by H, these are all constants, into e power delta S naught double dagger by R. This is also temperature independent term, there is no temperature here, and I have one temperature term, e power minus delta H naught double dagger by RT. Okay. Now, what I am going to do, I will take logarithm. So, ln K by T equal to, right, ln of this quantity kappa into KB by H, okay, plus if you take logarithm for this, I will get ln the delta S naught double dagger by R, and here I will get delta H naught minus delta H naught double dagger by RT. Okay, if I plot this in y-axis and 1 by temperature in the x-axis, okay, so if I plot ln K by T in y-axis and 1 by temperature in x-axis, observe carefully, this is very, very important. What you have to do, you measure the rate constant at various temperatures. Okay, you take a particular reaction, measure the rate constant at different temperatures, right, and find out K by T value and 1 by T value, and then plot ln K by T versus 1 by T. If you plot, see I have minus sign here, so you will get straight line with a negative slope. You will get straight line with negative slope like this. Okay, now listen, what is the slope? Slope is equal to minus delta H naught double dagger by R. So if you plot ln K by T versus 1 by T, you will get a straight line. From the straight line, you can find the slope. So experimentally, from the slope, listen, from the slope, you bring this R here, minus here. So what is delta H naught double dagger? Delta H naught double dagger equal to, okay, minus R into the value of slope. That's all. See, experimentally, you construct this graph, okay, and you will get a straight line. Measure the slope, and from the slope, you can find delta H naught double dagger. Then what is the y-intercept? Listen, y-intercept is equal to this quantity, that is ln kappa into KB by H plus delta S naught double dagger by R. Okay, see, both KB is Boltzmann constant, H is Planck constant, K is a transmission coefficient, all these are constants. Right? If these values are known, then from the y-intercept, we can calculate delta S naught double dagger. So, delta H naught double dagger and delta S naught double dagger, these two can be determined experimentally using this idea. Okay? Take note. Now, we will discuss reactions in solution. Okay? Reactions. Kinetics of reactions in solutions. Kinetics of reactions in solutions. Okay, so we'll discuss kinetics of reactions in solution. Yes, how to do this? Listen. How to do this? Listen, now we not only have reactant species, we also have solvent molecules along with it. Okay, so this is very important. In the gas phase, we have only reactant molecule. So reactant molecule combine, form activated complex, and activated complex form product. It's a very simple one. But now, in solution, you not only have solute particle, you also have solvent. So solvent going to play an important role. Okay, and what is the proposed mechanism? The proposed mechanism is same. Suppose I'll take two species A and B. They combine and form an activated complex in solution, and the activated complex form the product. Yes, as usual is right. Now, for this reaction, for this equilibrium, quasi-equilibrium, equilibrium constant is equal to, listen, instead of concentration, I'm going to use activity term. Activity of the activated complex by activity of the reactant molecule A into activity of the reactant molecule B. Now you know very well what is activity? Concentration into activity coefficient. So activity is equal to concentration of the activated complex, which is nothing but X double dagger, by concentration of species A, concentration of species B into their corresponding activity coefficient. We represent activity coefficient by the symbol gamma. Gamma of activated complex by gamma of the reactant molecule A and gamma of reactant molecule B. This is K double dagger. Okay, this is K double dagger. Now, you know very well from transition state theory, we know very well rate constant K is equal to kappa into KBT by H, okay, into this K double dagger. Okay, so if you substitute that, right, you will get, okay, this is the expression. What is that? Listen, I can write K is equal to kappa into KBT by H, right, into this K double dagger, right. Now, from the transition state theory, you know very well, rate constant is nothing but the frequency which with the activated complex transform into product into concentration of the activated complex, right? So, frequency with which it decomposes is nothing but KBT by H. Okay, I put that value here. What is the concentration of the activated complex? You bring all the term to the left hand side. So, you will get K double dagger, right, into, yeah, actually I made a mistake here. I should include this, okay. Let's check this. So, K double dagger into concentration of A into concentration of B into gamma of A into gamma of B by gamma of double dagger. Yes, this is the expression for rate constant. Okay, take note. I'm sorry, this is not rate constant, this is rate, right? Rate. As per transition state theory, you just refer the previous paper, you will get the idea. What is rate? What is rate? Rate is equal to the frequency with which the activated complex decompose into concentration. Correct. Frequency is nothing but KBT by H. What is the concentration of the activated complex? Yes, from this we can find the activated complex expression and substitute that value here. This is rate. Now, what is the experimental rate? Let me write the next page. Experimental rate is equal to rate is equal to rate constant into concentration of A into concentration of B. Okay, if I equate these two, you will get K is equal to, if I equate this rate and this rate, what will happen? Here we have AB, here we have AB cancel. So what we get is K is equal to KBT by H. Kappa is there, yes, kappa into KBT by H, Okay, into the terms. Each and every term we should write. AB cancel with K double dagger into activity coefficient of A, activity coefficient of B by activity coefficient of the activated complex. Okay.